right, if we look then at estimating the population mean, and there will be a key thing that you'll have to pay attention to. So on the test, I mix these guys all up, so it's not just a, hey, we're in this section, so we're always doing mean, or there's sections, so we're always doing proportion. You need to read and know what you're finding as you do each of these. So today we're going to look at estimating the population mean when we know the standard deviation of the population. Next time on Monday, we'll look at what we're going to do when we don't know the population standard deviation. So pay attention to what the wording looks like as you're doing these, because they will look very similar styles of questions. It's just a difference of what do you know and what are you trying to find. So this section presents methods for estimating a population mean. In addition to knowing the values of the sample data or statistics, we must know the value of the population standard deviation sigma. So when you know the population standard deviation, that can narrow things down a lot more as far as what we can do things with. So our notation that we've got, mu still stands for population mean, sigma still stands for population standard deviation, X bar is still the sample mean, N is still the sample size, E is the margin of error, that's that plus or minus part that we're going to allow it to be wrong by. Z of alpha over 2 is the z-score separated in an area of alpha over 2 in the right tail of our standard normal distribution. So notation is really not any different than what we've already had before. And so notice that what we'll have is we know the sample mean. You might also know the sample standard deviation, S. But if we're going to use this method, we have to know sigma. We have to know the population standard deviation. What we're trying to do is estimate that population mean. And so we're going to get that range of what is that values that we could have. The confidence interval then for estimating a population mean when you know the standard deviation. These things have to be met. The sample has to be a simple random sample. Again, if you have bad data, you can't do anything with it. So you've got to make sure your sampling techniques are good sampling techniques first. The value of the population standard deviation sigma is known, and either one or both of these have to be true. Either the population is normally distributed or the sample size is more than 30. And so that goes back to what we were looking at before when we're talking about the I've lost central limit theorem. Couldn't think of the name for a second. When we were looking at the central limit theorem, the fact that if you have a sample size more than 30, then any time that you're taking the mean of the sample means was the population mean. If you already had a sample that was a normal distribution, then if we took the mean of those sample means, it would also be the population mean. Didn't matter how big our sample size was if we were looking at those. So our central limit theorem is using that last little bit of information as we're applying it. So this is an application of the central limit theorem without it necessarily screaming, I'm using the central limit theorem in the process of where a lot of these formulas come from. It's based off it. So your confidence interval for estimating a population mean, if I'm trying to find mu, I'm going to take my sample size minus my margin of error. It gives me my lower limit, my sample, not the sample size, the sample mean minus the margin of error. The sample mean plus the margin of error gives me my maximum for that. So this gives me my range of what I'm going to have for my population mean. It's going to be somewhere between those values. The way we'll calculate out our margin of error. The margin of error is that z of alpha over 2 times the standard deviation of the population divided by the square root of n, where n is my sample size. And you can either express that as your interval, where you put that mu in the middle, and notice this time it's mu in the middle, not p, because it's trying to estimate the population mean. Or we can say it's the sample mean plus or minus the margin of error, or we can just put it as that interval. All three of these are expressing the same thing. Kind of depends on the situation, which way we'll want those. Most of the time, if it's reported in newspapers or in even in a lot of journals, if you're taking like a medical journal trying to talk about the information coming from some sort of medical survey and stuff that they've done, a lot of times they'll tell you what the mean is, and they'll say that plus or minus the margin of error. A lot of times if you look at polls on election polls, they'll say, 38% of the people support it, plus or minus 2%. Well, at plus or minus 2%, say it's really going between 36 and 40% is the true value that support this. Or sometimes you'll see it as that 36 to 40%. It's somewhere in there, and you'll see those confidence intervals. So it depends upon how they word it. All of those mean the same thing. Now, if we're trying to figure out that margin of error then this time, this E being your Z of alpha over 2 times the standard deviation over the square root of n, it comes from rearranging the equation of our central limit theorem for a sample of values. Look at where that was coming from on page 290. So on page 290, what we have is the equation of Z equaling x bar minus the mean over the sample standard deviation, or sorry, the population standard deviation over the square root of n. Well, my margin of error is that difference between the sample mean and the population mean. So x bar minus mu is the same thing as saying that is E. That is your margin of error. So if I'm trying to solve this for E, then the opposite of dividing all of this is to multiply by all of that. So my margin of error is my z-score times sigma over the square root of n. Well, that z-score that we're allowing it to be, we're saying we want our confidence interval or confidence value. That's where that z-score is getting to be. It's where that amount that we're going to have on our rate tail. And so this is just that same equation that we're looking at over here. So it's just rearranging that central limit theorem is where this is coming from. So everything, it's not like we're recreating something completely new. We're just rearranging what we had, which is why we had to meet the same criteria that we had to meet for the central limit theorem. Questions here? Okay, round off rule for confidence intervals. When using the original set of data, round the confidence interval limits to one more decimal place than is used in the original set of data. On the other hand, when the original set of data is not known and only the summary statistics are given, so you know the sample size, the sample mean, and the sample standard deviation, then you round the confidence interval limits to the same number of decimal places used for the sample mean. Now, again, I'm not making up new rules. It may sound like it's new rules when it's coming off to the round-off rules, but it really isn't. When we were back in Chapter 3, and we started off finding the mean and the standard deviation and all those sample statistics, the rule back when we were talking about finding the sample mean was you rounded it to one more decimal place than the data had. Well, if I've already rounded this value to one more decimal place than it already had, then I don't want to make it go out to more decimal places than what it already is. I already know where that rounding rule is, so I still keep the same rounding rule we had before, so you're still rounding it to the same sample mean. If, on the other hand, instead of giving you the sample statistics, if I give you the original data, I give you, let's say we're trying to figure out mean of student ages, and I gave you a sample of all the different student ages, and you had the original data, then it has not been rounded yet, and we're still applying the same rounding rule. We're going to round it to one more decimal place than what it originally had. And so you would get the same things. Whether I gave you the original set of 50 people and you were trying to find what that confidence interval looked like, if I gave you everybody's ages to just, they're 18 or they're 19, I didn't take it out to the nearest month or something, then you would round it to one decimal place. Well, if instead of giving you the original 50 data values, if I already rounded it and I said, okay, here's 50 data values, the mean age was 19.2, the standard deviation was whatever it is, then if I already rounded that for you, you don't want to re-round it again. You're going to keep it to that same one decimal place. So both of these are going to get you the same rounding rules both ways. But you have to pay attention of, do I know the original data set? If I do, it hasn't been rounded yet, so you round it to one more decimal place. On the other hand, if it's already been rounded, keep it to the same rounding that it already was. Questions there? So let's do an example. We look at page 353 and do number 24. On page 353, number 24, a simple random sample of 50 adults, including males and females, is obtained, and each person's red blood cell count in cells per microliter is measured. The sample mean is 4.63. The population standard deviation for red blood cell counts is 0.54. Find the best point estimate of the mean red blood cell counts of adults. So first of all, what do I even know? What is the 50? Okay, it's my sample size, so that's N. What is the 4.63? And is that mu or is that x bar? Okay, it's my sample mean, so that's your x bar. And what's the 0.54? Okay, population standard deviation, so that's sigma, it is not S, which is 0.54. Okay, so that's the data we already know. So then on part A, what is the best point estimate of the mean red blood cell counts of adults? If I asked you, so what is the average number of blood cell counts, red blood cell counts? From the information we have, what would you guess it to be? Aaron, you're whispering the answer. Why would you go with 4.63 as being the mean for all the entire population? Okay, it's our best guess. It's the sample population. Now, are we going to be exactly right? So this is our best guess. I shouldn't say it equals. I should probably say it's approximately. My best guess is it's going to be 4.63. I'm guessing that since I've got a good sample, and it's a sample size of 50, so it's definitely more than the 30, I'm guessing it's going to be pretty close to the true population mean. Now, on this one, do I know the population standard deviation? This has been done. Red blood cells has been taken care of so many times. We've got a pretty good guess of what it's going to be. Standard deviation is 0.54 as the population standard deviation. Now, I want to construct a 99% confidence interval estimate of the mean red blood cell counts of adults. So I want to be 99% confident. And I'm wanting to construct my confidence interval. So my best confidence interval estimate for the population to mean. So that's telling me I'm going to use the E is the Z of alpha over 2 times the standard deviation over the square root of N. So if that's the case, what is Z of alpha over 2 first? Okay, where are you getting the 2.575? Okay, you're looking up that 0.995 because alpha is the 0.01, alpha over 2 is the 0.005. That's the area to the right. And so when you're looking at your thing, we're wanting our area to the right to be 0.005. So half of 1% is the area in that right tail. So that Z-score is going to be the 2.575. And you're looking up the area on the left being the 0.995. Sigma was 0.54, N was 50. Going to give you a moment to use your calculators and find that value. Does that look like what you're getting? Okay. Now I need to figure out my rounding rule. If I'm looking at doing my rounding rule, did I know the original data, or was I given the original summary statistics? Okay, given the statistics. So how many decimal places should I round this? Going with 2? Okay, 2 would be a good answer because that was rounded to 2 decimal places, therefore I still have to just keep it out to 2 decimal places. So what will this round to? We're going to round that to the 0.20. Now, what is my confidence interval? How would I find my lower limit and my upper limit? I'm off by 0.20, but off from what? Okay, I'm off from the mean, because the mean is my best guess, and it might be a little above by 0.2, or it might be a little below by 0.2. And so my interval is going to take my sample mean, which is the 4.63, and it's going to have that plus or minus 0.20. We're going 2 below, means it's going to be the 4.43. 2 above is going to be the 4.83. And it's the mean, the view is the value in the middle because that's the population mean that we're trying to estimate. The population mean is going to be somewhere between 4.43 and 4.83 red blood cells per microliter, I think, are my units. Questions? Now, part C on this question. The normal range of red blood cell counts for adults is given by the National Institutes of Health as 4.7 to 6.1 for males and 4.3 to 5.4 for females. What does the confidence interval suggest about these normal ranges? So let me ask this question. If males are somewhere, so this was ours. Let me ask first this question. Was this for males or was this for females? It did say. It was for both. So this is a combo of both. Do what? Your females are in here. Okay, so if we look at, this is the range of ours from, saying a combination of both was in there. If the males are 4.7 to 6.1. Now, what does it say when I tell you, let me ask this question before I even ask the next part. What does it mean when I tell you that the mean number of red blood cell counts per microliter is between 4.43 and 4.83? What's that even telling me? Does it tell me that sometimes the mean is 4.5 and sometimes the mean is 4.7? It's not saying that sometimes it's this and sometimes it's that, and it's anywhere between. What am I actually saying? I'm saying that I am, in this case, 99% confident that the true mean of the entire population, when we're talking about males and females together, is somewhere in between these two values. It might be 4.7, it might be 4.8, it might be what was the middle number, 4.63. It's somewhere in there. I don't know where. So when I say that the confidence interval is somewhere between 4.7 and 6.1, are these numbers here in there? Okay, 4.7, we've got some that are a little below that. We don't go all the way up to 6.1, but if we're saying we're confident it's in here somewhere, most of it's covered. You've got a little bit that's going down below. But when we, and this was men, when we look at the women are between 4.3 and 5.4. What do you know about them? Let me ask it this way. Is this in here? Is the 4.43 in there for the females? Is the 4.83 in there for the females? All of this is inside of here somewhere. So if I'm telling you the mean of the combo of both of them is in this, somewhere in here, all of my confidence interval I have here is inside the females. Most of this is inside the males, but if we had females, what's it look like the females are doing to the red blood cell counts? Does it look like women are higher or lower? It looks like women are lower. So it looks like having women in there is going to bring the mean down some. And so by having this being a little lower than what the males is, it kind of gives me a good idea that there are definitely females in there. Because it's completely inside the female range, and most of it's inside the male. I mean, we're missing a little bit when we do that 4.43 to 4.7. So some of it's missing, which definitely, again, is just really, to me, saying that there's some females in there to bring that down. It's pretty confident that we're probably okay. It looks like our numbers sort of fit well with what we had. The book goes on, how do they word everything? It says the confidence interval is mostly within the range for males and is entirely within the normal range for females. The mean is roughly within those normal limits then. So when I'm trying to say that I'm 99% confident that the true mean is somewhere between 4.43 and 4.83, I'm okay. Now, I want you guys to do some by hand, because I want you to get an idea of what it is you're working with, what you're doing with these kind of problems. But looking at how you have the calculator that can help you out with these. If we're doing these problems, you're going to use the Z interval. So you're going to go into statistics. So you're going to go to your stats, arrow over to tests. You're going to do number 7, which is the Z interval. Now, remember last time when we were doing things, we came down to A to do the one. Oh, you can't see my stuff. Last time we went clear down to A to do the one proportion Z interval. So we were still using the Z scores when we were talking about proportions. Now we're doing number 7, which is the Z interval, because you're taking a Z score and you're going to get an interval of values. So recognizing that what you're trying to go for is going to be important. So once you hit enter on there, now the question is, do I have the original data or do I have the statistics? If you have the original data, then when you get to here, the next question is, what is the population standard deviation? Where did you put it? So if you put it in list 1, that's where it's going at. Each one of them is a frequency of 1, your confidence level, and then calculate. But on the other hand here, we were given the sample statistics. So you're going to go over your stats. Again, the next question is, what was the population standard deviation, which was what this last problem? 0.54. What is my sample mean? What was the number in my sample? Which was 50 this time. How confident do you want to be? We want to be 99% confident. And then you can calculate. And it's going to give me my confidence interval, which is saying we're 99% confident that the true value for the mean is somewhere for the population mean, not even just the sample mean you already know. We're trying to guess, take the sample and tell something about the entire population, is somewhere between 4.43 and 4.83. Questions? And I guess I did forget to ask on this problem, did we meet the criteria that we had to have to be able to use this? Did we have a good simple random sample? Does it tell me in that? Okay, it tells me at the very beginning I have a good simple random sample. did we have, what was the second one? Was the value of the population standard deviation known? Did I have a sample size of either larger than 30 or coming from a normal distribution? Which piece? Okay, we had more than 30. We had a sample size of 50. It doesn't tell me anything in here about whether or not this comes from a normal distribution or not. But because my sample size was more than 30, I could ignore that. Oops, I don't have another example for you guys to do. Okay, looking at figuring out how big does the sample mean need to be then. If I come back to here, if I want to solve this equation for n, well, to get n by itself, I would multiply both sides by the square root of n and have e times the square root of n equaling the z times sigma. So to get n by itself, I would have to divide by that margin of error and have the square root of n equaling the z times sigma over e. What's a sigma? Opposite squaring things is to, opposite square rooting each things is to square it. And so my sample size is going to have to square the value of the z of alpha over 2 times the standard deviation of the population over the margin of error. So when you're trying to find your sample size, that's exactly what you're going to use. So it's just rearranging that equation. So it's not a different equation, it's just rearranging the same equation to look different, which again came back from our central limit theorem. And so to figure out how big does my population need, how big does my sample size need to be to give me the confidence level I want and the margin of error that I want. How many people do I need to have in my survey, or how many M&Ms do I need to have in my sample? So what is it that you're looking for? This will be what you calculate out. Our round-off rule for sample size, can we sample half an M&M if we're going to the factory of M&Ms and we're trying to do a quick test to make sure that they're doing a quality control test? Can you sample just part of an M&M? No. You either look at the M&M or you don't look at the M&M. You're not going to look at just a part of the M&M if it's part of your sample size. And so you're going to have to count whole pieces, whole values. Would you rather have your sample be too big or too little? Too big is better. And so you're going to always round up when you're trying to figure out your sample size. So if the computed sample size n is not a whole number, round it up to the next larger whole number. So let's look at number 16 and figure out how big does my sample size need to be. So for failure times, how many integrated circuits must be randomly selected and tested for time to failure in order to estimate the mean time to failure? We want 95% confidence that the sample mean is within 2 hours of the population mean, and the population standard deviation is known to be 18.6 hours. So my formula we're using is that n is, make sure I get it completely written the same way, the z of alpha over 2 times sigma over the margin of error, quantity squared. What do we know on number 16? Okay, population standard deviation sigma is 18.6. What else do we know? Sample mean is not 2. Confidence level is 95%. So if I want to be 95% confident, what's that going to find for us? Okay, it's going to help me find my z. So alpha is 0.05. So we're going to find z of the 0.025. That is the 1.96. That is saying that if I want to have 95% confidence that half of it's in this side, half of it's in this tail. I want this z-score that gives me the 0.025 to the right, which means the 0.975 to the left, which is the 1.96. It's one of them you've done several times already. So now if we're using the z being 1.96, what else do we know? What is E? Why is E 2 hours? Because what? Because it's the only number left, and this is the only variable left? Yeah, I need a better reason. What did the 2 hours stand for? I'm 95% confident that what? What is that 2 hours? Okay. Looking back at how it words the question, we want 95% confidence that the sample mean is within 2 hours of the population mean. What does E stand for? Margin of error. It's asking how far off can I be? How wrong can I be and still be okay with my answer? As long as I'm only 2 hours wrong, I'm okay with my answer. I can be 2 hours above, 2 hours below, and that's all the further off I want to be on this problem. That says that's my margin of error. My margin of error is asking what is the difference between my sample mean and my population mean. That's what it's asking for. I should say the absolute value of that. That's what it's asking. What is that difference between the true sample mean, what's the difference between the sample mean and the true population mean? How far am I allowing that to be wrong? In this problem, I'm allowing it to be wrong by 2 hours. That's going to be my plus or minus amount when I get done with this problem. So when I put that into this problem, we're saying we're going to take the 1.96 times the 18.6, divide that by 2, and square that whole thing. Don't forget the square. That's probably the most common mistake in this problem, is that you guys ignore that little detail. And so when you do all that arithmetic and square it, what do you guys get? Why you have braces around your answer? It's the right answer. I don't know why you have braces. That's odd. That one didn't. Huh, must have been. Okay. It was. Did you get it? Okay, so you guys are getting 332.26. If you're getting 332.26, what would be my sample size? We always round up, so I need to have 333. So in this case, I would need to have 333 circuits that I'm going to test to figure out their time to failure, wasn't it? Yeah. I'm going to test 333 circuits to figure out their time to failure, so that I can figure out what is the average time to failure for these circuits within 2 hours. Questions? So that I can be 95% confident that the true time to failure is whatever that is within 2 hours, that plus or minus the 2 hours. Now, a lot of times, pollsters are going to do the same kind of thing. They want to figure out they're going to be 95% confident. Most polls that you read in newspapers and stuff are plus or minus a certain amount. and then they figure out, well, how many needs to be in that sample to make that happen. All right. I haven't printed off your extended problems yet because most of them aren't going to make sense to you quite yet, since we need to make sure we finish a little bit more of the section. But the test is going to be next Friday on March 27th, so I'll have the extended problems for you guys Monday. Have a good spring break. Maybe I should say have a good 4-day weekend.